Alright, hello. Anyone who's watching, hello. Um, this is going to be 2D flow simulation over a 2D cylinder in ANSYS Fluent. So we're gonna click and drag here, put this here, and we're gonna click on geometry, go for 2D, and we're gonna right click, and then we're gonna enter new design modeler geometry. That's the one that I'm gonna use. You're free to use another one. This one's just pretty simple and easy to work with when you're starting. Then plus Z direction, then we're going to click on the XY plane to start our sketch, and then we're going to go into sketching, and then make sure your units are in meters. Well, for this project, it'll be in meters. So then we're going to do a rectangle here, just rough rectangle. We're going to center it in a second. We're going to go to constraints, and then we're going to click on symmetry. So we're going to click on this middle line, so the vertical y-axis. Click on the left and right, and then it's centered, symmetrical to the y-axis, and then we're going to do the same thing for the x-axis, so top and bottom lines. And then there we go. Now it should all be symmetric. So then we're going to dimension this square slash rectangle. So top line, right line, and then we're going to make this into a 50 by 50 square test section area. And then what we're going to do now is we're going to go into draw, and then we're going to hit circle, and then we're going to make this circle right here, and we're going to dimension this circle. It's supposed to be 1 meter diameter, at least for this for this case, for this project. And then once we've done this, we're ready to generate our sketch. So we're gonna click on concept. We're gonna click on surfaces from sketches. Then we're gonna hit this plus sign, and then we're gonna click on the sketch. Everything should be yellow, and then we click apply down here. So then it's like sky blue. And we're gonna click generate. Alright. And then now we're ready to move on into our meshing. So we're gonna exit out of this, and then we're gonna go here, and then we're gonna right click on our mesh to edit, and it's gonna take a little second to bring up the meshing section. And then okay, there we go. Once it pops up here, we're going to start with our mesh. I'm gonna click mesh here. I'm gonna right click insert method mesh. And then for geometry, we're gonna click on this face here. And click apply. And we're gonna do triangles method. And then that should be it. And then now we're gonna click generate, and just to see what we're working with here. So as you can see, not very fine. We need this we need to refine this a lot more. The good news is that it's getting finer towards the cylinder, so that's good. So we're gonna right click on our mesh, insert, and then sizing. And so we're going to click on this edge, and we're going to click on the cylinder and click apply. That's for our geometry. And we're going to do element size, and then we're going to do 0.005 for that. It's a little, actually, yeah, that's fine. And then for capture curvature, we're gonna go no, and then behavior, we're gonna go hard. And after that, we should be cool. And then one last thing that we're going to input is we're going to insert an inflation here. The geometry is we're going to click on this, and hit apply. Then we're going to go to geometry selection, click on boundary, and you're going to click, you're going to do this edge, and click on this cylinder, and then click apply. That's going to be our boundary. I'm going to click on smooth transition and change this to first layer thickness. First layer height, I believe, should be 2. Maximum layers is 100. And then growth rate is going to be 2.5. Okay. And then after this, we should be all ready to generate. So we're going to click on generate. Might take a little while. Hopefully it doesn't take too long. Oh, there we go. Awesome. We probably made our mesh too fine, but it's worked fine with my project so far. It's worked pretty fine. So this is really what we need, is just this like refinement around the cylinder. But then the rest of this, we need to adjust this a little bit. So I click on here on our general mesh, and then we're going to change our element size to 0.15. That's all we're going to do. Yep, that's all we're going to do. And then we're going to click generate again. And this time, hopefully it doesn't take too long. Feel free to fast forward to when the meshing is done. I'm going to mute while that's going on. Alright, so our meshing is done, and then we can zoom in to see we have a really fine mesh, and then as we zoom in around the cylinder, we have a very fine mesh, which hopefully will give us accurate results. Alright, so we're done with the meshing. We have one last thing to do, is we're going to click on edge, make sure you have your edge selected. We're going to click on these and we're going to name these. So hit N on your keyboard. This is going to be your inlet. And then this is going to be your outlet. And then we're going to name these top and bottom ones. So just click Control click. We're going to name them symmetry. And then we're going to click on the inside here. And we're going to name this, we're going to cylinder. There we go. Then now we can exit out of this meshing. One second. And then we're gonna update this before we go into our setup. It's taking a little while. Alright, so now we can go ahead and go to our setup, right click on edit, and it's going to show this right here. So what I'm gonna do is double precision. Then we're gonna do 3 solvers. Yeah, we're gonna do 3 solvers. Actually, do 4. 4 solvers. If your computer can, work with 4 solvers, by all means go ahead. It might take a little longer if you do 2 solvers, but it's definitely still computable. If that's the right word to use, but definitely still doable. Alright, so this is how we know that our meshing was complete. You should be able to see this inlet and outlet happening right there. Okay, so first thing we're going to do is we're going to go to models, and then we have 3 cases that we're going to be going over. So we're going to do Inviscid, we're going to do Laminar. Now what I'm going to be doing for this case is K epsilon for our turbulent case, but I'm first going to go over Inviscid. So for our project, right here, it says to use inlet velocity 5 meters per second for Inviscid flow. So that's what we're going to go ahead and do in this case. So we go to materials, you want to check your air. Air is fine. I don't know why it's looking like that, but that's fine. It should be 1.225 and then 1.7894 for your viscosity. So then we're going to go to boundary conditions. We're going to double click on inlet, and then we're going to change this to 5. We're going to apply, and we're going to close. Alright, and so before we move on, we want to go to our reference values and make sure that ANSYS is computing from the inlet, so it'll have that 5 velocity that we just inputted, so it's going to start calculating from here. And then we're going to go into methods under solution. And then for scheme, we're going to do simple for the Inviscid case. And then for pressure, we're going to go presto. Okay, and that should be fine. Monitors, we're going to go into residual. We're going to add like 2 more zeros here. We're going to hit OK. Actually, we can do e to the negative 6. E to the negative 6. And we're going to go out of monitors. And then we should be good to start initializing. So I'm going to go to initialization. And then this is not an obligation to do, but I upped my iterations of initialization to 35. You don't have to do that, but it is okay. Like you can do like 15, 20. That's okay. And after initialization is done, we're gonna double click, and I'm gonna do my number of iterations to be 1,000. And we're gonna hit calculate. And hopefully it doesn't take too long. Yeah. So feel free to fast forward through the calculation part. I'm gonna go ahead and mute myself. Feel free to fast forward. All right, so now that our calculation is complete, we can go ahead and generate our contours. And go to graphics, under results, and then double click on contours. We're gonna select all of these. There we go. Select all of these, and then we're gonna do velocity. And we're gonna hit save and display. And then here you can zoom in and really look at what's going on. So you have 2 stagnation points as dictated by the theory that we know that we're supposed to get. And almost 2 times our U infinity free stream velocity there. So that is good. And then showing your pressure contour should be, yep. So max pressure at the stagnation points, the lowest pressure at the maximum velocity. That is all within expectations. So that's good. And then we're gonna go ahead and to show the, actually let me change this to velocity really quick. Right, and then we can go ahead to show the streamlines. There are 2 ways that you could do it. So the first way, which is the way that I'll be showing you here, is to just double click on path lines down here. I'm gonna move this. So under solution or under results, graphics, then path lines. You double click on that, and then you can click it release from surfaces. It's gonna be just the inlet. Then you go here by color by, switch it to velocity, and steps we're gonna do 3000. I'm gonna see why in a second, but then this is what ends up happening. We have something nice like this going on. So that is one way that you could do it. The other way that you could do it is by, close this, minimize this. So you can go to results here, and then you could, actually I'll do this one time for the Inviscid case. So once you have everything pulled up in results, and once it finishes loading, you basically just do the same thing I just did, but up here there's a button that if you hover over it, it'll say Streamline. So you click on Streamline. You can, name it if you want. I'll just keep it Streamline 1. You can click Surface Streamline. Surface, you're going to click Symmetry 1. And then number of points, we're going to do 3000. Preview it if you want. I don't know if that's going to, yeah. Like that, number of points. You can increase it if you want. I don't think that's necessary, but then you're going to click apply. Then you're going to see all the nice streamlines going across from left to right. If it wants to load fast, that would be nice. And there we go. So now if you zoom in, you can notice the streamlines happening very nicely. Just to be super accurate. So yeah, those are the 2 ways that you can show your streamlines. Now we're going to exit out of results. Then we're going to go back to the fluid flow. And then the other thing that we need is to plot the velocity distribution and the coefficient of pressure distribution. So I'm going to show you how to do that next. So you're going to go under results, go to plots, XY plot, and then you're going to click on just the cylinder. That's all we need is just the cylinder. And then you're going to click on velocity. And you're going to save plot, and then that's how it should look. Right? So it should look like, you have 0 at one stagnation point. Then it's only going to show like half of the cylinder, right? So like one stagnation point at the front of the cylinder, one stagnation point at the other end of the cylinder. Yeah, so if you see like negative 0.5, then to 0.5, that's the diameter. So we know this is the top half of the cylinder. And it's going to be the same in the bottom half of the cylinder, theoretically, ideally. All right, and then to show the coefficient of pressure, you're going to go to pressure, and then under static pressure it says pressure coefficient, and that's what you want. You're going to save, plot, and then there we go. Which is consistent with theory, which your maximum CP should be 1, and then your lowest should be -3 in the Inviscid case. So that's consistent and really good. So yeah, I like always having my contours, so I'll just put this there. All right, and then if you want to merge your streamlines and the regular contour, you can go to Scene, and then you can click on contour and then click on path lines. I'm going to put this transparency up to like 50. And then you can click save and display. And then you have the contour as the background with the streamlines there, which is really cool to watch. It's really cool to see. Yeah. And so I think last thing for with regards to like reports and stuff like that, what you need. So you're gonna go to reports and you're gonna double click on forces in order, and this is going to be in order to get the drag coefficient. So I'm gonna click on the cylinder. Your drag coefficient is going to be in the x1, y0 direction, so that's going to be in the vertical direction from, horizontal direction from like this line, encountering the cylinder that way. I'm gonna click print, and it should show down here, right? And so in the Inviscid flow, theoretically it should be 0, but this is like 0.002, so that's like almost 0. It's near 0, so that's good. It's never going to be in reality exactly 0. So this is fine to see. And then that should be everything for the Inviscid flow. So then we're gonna go ahead for models. We're gonna switch viscous Inviscid to laminar and click OK. And that's all we gotta do with models and materials. Some people choose to change their densities and viscosities with um with like adjusting a Reynolds number. You can do that, or you could just adjust your velocity and like find a your laminar stuff like that. So using the Reynolds number, what I did was I went into the inlet, I checked my Reynolds number. So in our class for aerodynamics, the critical number for the critical Reynolds number for going from laminar to turbulent, we usually ignore the transitional region, which is like from 300 to like 500,000. So I did checking my Reynolds number. I did Reynolds number of 300, a little over 300,000 for the viscous laminar. Gave me what I needed. And so that's what I'm gonna go ahead and continue doing. So reference values is fine. Yeah, reference values are fine. And then methods. For the laminar, we're good with simple impresso. For the other one, I'll show you later. Monitors, residual is fine, like I said. And then we're going to go ahead and initialize as well. Alright, and then we're going to double click, we're going to run the calculations again. And then feel free to fast forward until that is done. I'm just going to mute. Alright, so our calculations should be done. Calculations should be done in a couple of seconds, hopefully. Okay, there you go. So then we have this wake region right here, which is, whoa, okay. Have this wake region right here, which is characteristic of a Reynolds number this high. You have, the up and it's going like that. So it is characteristic of a Reynolds number this high, which is good. I don't know why it's being so slow. I'm just gonna leave that alone. Okay, there we go. So as you can see, this is the velocity contour with the streamlines. And then you can double click on your contour and then you can change it to pressure. Static pressure is all you need, so no need to like look at the dynamic pressure and all that stuff. So this is pretty cool here, you know. And then yeah, and then okay, so the plots here over the cylinder, you can look at the pressure coefficients. I'm gonna do that, and then this is what it's gonna look like. Just because we have like a more chaotic like region behind. Um, Hold on, there we go. Just because we have like a more chaotic region, so it's not gonna be completely symmetric like the other one. And then we can look at the velocity, and then this is good because of no slip condition. The velocity is going to be 0 along the surface of the cylinder because of no slip condition, the existence of a boundary layer, flow separation, and um, viscous forces. The particles stick to the cylinder, and the velocity along the surface is 0. And then when you're done with all of these, you want to click on write to file, and then pick like a folder, and you want to put those in Excel into one graph for all three cases. So you want to save these as you go. And then lastly, for the laminar case, go here, and then this is again down here, that's going to be for your drag coefficient, which is all we need. So it's going to be 0.44157,148. And you can use this pressure if you want to do hand calculations. You can use this force here to calculate and then divide it by your dynamic pressure, which is 1 over 2 rho infinity u infinity squared times your area to find what you need, or like your theoretical. And it's going to be close to this, hopefully, when you do that. And then lastly, we're going to go back to models. We're going to double click on viscous laminar. We're going to do K epsilon here. We're going to click OK. And then the only thing we need to change here is our inlet velocity. I chose a velocity of 12 meters per second. That gives me a Reynolds number of 821,000 approximately. So that's good. We're well beyond the critical Reynolds number of 500,000. So that's good to know. And we're going to close out of that. And then the next thing we want to do is we want to update our reference values, because if you notice here, your velocity 5 meters per second, it stayed there. So don't, hopefully you don't get tripped up by that, but it would trip you up if you're not careful. So you want to, hold on. And then, ooh, it should have updated. And I could apply a couple. Oh, wait, hold on. I searched the wrong thing. This is N5, and then this is 12. There we go. Don't do what I just did. Okay. And then we're gonna click to like symmetry, and then we're gonna click back to inlet. There we go. That should be 12 now. And then for methods, I'm gonna switch from simple to coupled. And then instead of pressure, presto. Actually, presto is fine. Well, let's see. So second order, these are just gonna give you like more accurate results here on the iterations and stuff like that. I've done it with the simple presto, and it also works. So either one, it's just depending on which one gives you the best results. I'm gonna use it for the sake of like time in the video. Don't want to waste your time, but these like calculate faster is what I found for my. And then this is fine. It's just saying that you change your settings. So you click OK, you initialize, and double click on run calculation, and then you want to calculate again for the last time. And yeah, so there's a couple ways that you could do this really, because you could also go to models, you also go to models and go from K epsilon to K omega, I believe it was. And you can use different models. Just if this one doesn't work for you, then use other ones. And with the methods, coupled and second order will give you very accurate results, but it'll just take longer. And I don't want to. I don't think my computer can handle that in the moment. Um, but yeah, it just takes a while. I've watched some videos of this that take like an hour to calculate, so it just takes a while and a lot of patience. But yeah, feel free to fast forward. I'm gonna mute myself now. Alright, so our calculation should be done here. Okay, awesome. So then we can go ahead and check our contour again. So we're going to go to velocity contour, save and display, and then there we go. So you have a lower angle of separation, so it separates um, later. It has a harder time separating because the turbulence is energizing the flow, and so that helps the molecules grab a hold of the cylinder for longer before they split off. And so we have that, and then again with the streamlines, you can do the scene, the path lines, and everything. Your pressure, you only need static pressure, so you use static pressure here, like that. And then lastly for the forces, so plot velocity, velocity magnitude. So this one should also be 0 because of viscous forces and the no slip condition. And then for pressure, pressure coefficient, save plot. So it should be looking sort of like this. And that should be everything. Lastly, like the forces, new print, and then this is going to be your turbulence here. And yeah, that should be good. Thank you for watching. Hopefully this was helpful, and have a good day.